So for our pendulum, we had an equation of motion that didn't look like the differential equation we knew the answer to. And that was because we had s over here, our arc length, and we had theta over here, an angle. And not just theta, but sine of theta. So this wasn't in the form we needed. But what we can do is use the small angle approximation to say sine of theta is approximately equal to theta, as long as theta is small, say less than 10 degrees or so, and it's in radians. And that means we can then relate our arc length, which in general for a circle is going to be the radius of the circle times theta. In this case, we then are solving for theta. That would be theta equals arc length s divided by r. Well, the radius of the circle that the pendulum is moving in is the length of the string, L. So now, instead of sine of theta, I can just say theta, and I actually need the same coordinate on the left and the right, so instead of theta, I say s over L. So we have a new equation here. The second derivative of our arc length with respect to time equals negative g over L, where L again came from the conversion from theta to arc length, times s. This is actually the form that we know how to solve. We're solving this through recognizing our differential equation and then being able to write down the correct answer. Remember that the general form of any type of simple harmonic motion is that the second derivative with respect to time is equal to some negative some constant, where that constant's actually omega squared. So in this case, omega is then square root of g over L. So we see in this case that we can use simple harmonic motion to describe how a pendulum is going back and forth. But we've gotten here by using the small angle approximation. So this is pretty important, and one of these cases where modeling is incredibly important. The only reason we're allowed to model the motion of a pendulum as simple harmonic motion is because we've used the small angle approximation. So actually, if you want to talk about the motion of a pendulum for any angle, you don't know how to do that. That's really, really hard, really complicated, way beyond the scope of intro physics. But as long as we model the motion as being for small angles, it is then valid to use the approximation of the small angle approximation, and then we get to an equation which defines simple harmonic motion. So, simple harmonic motion is a model. Now, where we're going to see this appear is any time we have a system with a restoring force that's linear. So restoring force means the force is always back towards equilibrium, right? There's an equilibrium position and you always have a force that pushes back in it. And linear in this case means proportional to position, or the distance you are from equilibrium. And again, that could be x, that could be y. What we just saw with the pendulum is that we can be talking about arc length. So if this is true, it's simple harmonic motion. If it can be well approximated as linear, it's also simple harmonic motion, and that's how we got here for the pendulum. So there are going to be times that you might talk about simple harmonic motion where it's not really a law, but we've gotten here through approximation. So always talk about simple harmonic motion around an equilibrium position. So this should be a stable equilibrium point. The forces should return your object to that position. And what's really helpful is when you set the zero of your coordinate to be equilibrium. Otherwise, again, physically it will work, but the math will be incredibly complicated. Now, one thing that always comes up, and again, the math gave us this, is that frequency, either f or omega, and period, are independent of amplitude. You can start it with different amounts of velocity, different energy, different position, and you're always actually going to have the same period, the same behavior in time. Now, this is amazing, and it's always going to be true for simple harmonic motion. It's not going to depend on all of the variables that you expect it to. So mathematically, we're always looking for an equation of motion where the second derivative with respect to time of some coordinate is equal to negative, that's the restoring force, bringing it back to equilibrium, times some proportionality constant c, And again, it's a collection of constants that come from the physics times u, again, the position itself. So this is by default the restoring force, must exist. And omega, that angular frequency, is going to be square root of c. So you're looking for that those collection of constants that then tells you what that angular frequency is, and it doesn't depend on initial conditions. Initial conditions come into determining your amplitude and this phase constant. So you have two different constants that are determined by your initial conditions, which is where you started it and how fast was it going at the beginning. What direction it was going as well. Excuse me, that's also important. And right now, for simple harmonic motion, mechanical energy is conserved. Later, we're going to talk about some variations on this where energy is not necessarily conserved, or at least the motion looks a little different, and that isn't technically simple harmonic motion. So simple harmonic motion, energy must be conserved. So this model does not apply if you actually don't have a linear restoring force. And again, that includes the pendulum if the small angle approximation is not valid. That's also going to include any situation where you have a drag force, that now you have additional forces that don't depend on position in a linear way. So here is then the summary of everything we know about the pendulum as long as we are talking about small angles. So we've used the small angle approximation to get to this equation of motion, which is in the form we know how to solve. And based on this, we can then say this arc length position has our normal cosine form. Now, if we want to then convert over to angle, there's this conversion where S, our arc length, is equal to L, the radius of our circle, times theta. And again, we have been talking here about small theta, so don't forget that. And now we actually can talk about how it's moving in terms of theta. That our theta as a function of time still has an amplitude where now it's maximum theta, cosine of omega t plus phi naught. And in this case, omega is square root of g over L, and we could also write that as 2 pi f. You could also communicate t, capital T, period, in terms of g over L. Now there's one thing that's really important here that I want to stress. These are not theta, right? So part of why we've written this as phi naught. This is not your initial angle. This isn't a typo on my part. That remember that this is your phase constant that can be between 0 and 2 pi, or negative pi and positive pi, negative 180 degrees and positive 180 degrees. And that tells you where you are in this sinusoidal motion, right? So where are you in this cosine starting at 1, going down, crossing, coming back up? This is not your initial angle. Your initial angle would actually have to be converted into your amplitude and this phi naught. So if you start it at some initial theta and you let it go from rest, well, actually that is phi naught equals 0 and theta max is your theta initial in that case. So please be careful and note that we're using different Greek letters here because these are actually unrelated angles per se, that this is a mathematical theta, not a physical theta, and then theta is our, mathematical angle, and then theta is our physical angle. So hopefully that's clear from the notation. That's really important. And again, the only difference between talking about arc length and talking about theta when we're talking about our pendulum, as long as it's small angle approximation, because again, we can't model it otherwise, is just that you've changed what your amplitude is.